Hey everyone, welcome back to the Environmental Science and Engineering Podcast channel. Make sure to hit that subscribe button if you're into this kind of stuff. Today, we're going to get into something pretty crucial, safe drinking water, something we all kind of take for granted, right?
Yeah, for sure. And going into this, I was really struck by all the historical stuff you dug up about how people figured out how to make their water safe. It's a pretty crazy story when you think about it.
Yeah, it is. We've got a ton of material from like ancient methods to modern tech. So our goal is to really unpack all of that, see how it's all connected, and understand how it's shaped what we drink today.
Yeah, absolutely. It's like a journey through the evolution of drinking water disinfection. I think
Yeah.
it's going to be pretty eye-opening.
So let's jump right in. Even way back in ancient times, before people even knew about germs or any of that, it seems like they knew that, hey, not all water is the same. What were some of the things they did?
Well, think about it. They didn't have microscopes or anything, right? But they still did things like boiling water. Makes sense, right?
Yeah, totally.
And they also used sand filtration, basically passing water through sand to try and clean it up. And they even figured out that leaving water out in the sun in containers helped.
Huh. That's actually pretty clever. So even without the science, they had these sort of intuitive ways of making their water safer.
Exactly. They understood something was up, even if they couldn't see it.
Right, right. Okay, so let's fast forward a bit to the 1850s. We've got John Snow in London dealing with that massive cholera outbreak. Talk about a turning point.
Absolutely. I mean, think about it. Over 500 people died in 10 days, all because of this one water pump. It was horrific.
And the prevailing theory at the time was miasma.
Yeah, the miasma theory. Basically, they thought diseases were caused by bad air.
So how did Snow challenge that? I mean, his work was groundbreaking, right?
Yeah, totally. He basically went out and mapped all the deaths. He was super meticulous about it. And what he saw was this like really clear concentration of deaths around this one pump on Broad Street.
So that was a huge clue, right?
Yeah, it was. And then he went even further. He actually traced the contamination back to this like leaky cesspool that was near the well that fed the pump. Like a really early example of detective work, like a disease detective.
So he's basically like the OG epidemiologist, right?
Right, right. And here's the key thing. He hypothesized that cholera was spreading through the water, not through the air. He was like, it's the water, stupid.
Huh. Love that. So he goes against the whole miasma thing, which was a pretty radical idea at the time.
Yeah, totally. And what did he recommend? Remove the handle from the pump. Simple, but effective. And guess what? It worked.
Seriously, just taking off the handle.
Yep. September 7th, 1854, they took the handle off the Broad Street pump, and the cholera cases started dropping. That moment is considered the birth of modern epidemiology. I mean, think about how huge that is. It completely changed how we understand disease.
Wow, that is huge. So we go from blaming bad air to understanding that there's something in the water that can make you sick.
Yeah, it's like a paradigm shift in our understanding of public health.
Totally. Okay, so then a few decades later, we've got Louis Pasteur coming along with his germ theory, right? This seems like another big piece of the puzzle.
Right, right. Pasteur comes along in the 1880s, and he basically proves that microorganisms are the real culprits behind a lot of diseases. So now we've got the why. It's these tiny, invisible organisms that are making people sick.
It's amazing to think that something so small could cause so much havoc. And around this time, filtering water starts to become more common too, right?
Right. Filtration, using things like sand filters, became increasingly popular in both Europe and the US. It was a way to physically remove stuff from water.
I guess it makes sense that they would start with something like that.
Yeah, it was a logical step,
Yeah.
and it definitely helped improve the clarity of the water and get rid of larger particles.
So problem solved, right?
Not so fast. While filtration helped, it wasn't enough to completely eliminate those microscopic disease-causing bugs. The epidemics kept happening.
So that's where the idea of chemical disinfection comes in, right?
Right.
I read that someone actually suggested adding chlorine to water all the way back in 1894.
Yeah, that's right. It was a pretty bold idea at the time, but it would eventually become the most common method for disinfecting water worldwide.
I guess, in a way, it's kind of obvious. We all know that bleach kills germs.
Yeah, but using it to treat drinking water, it was a big leap.
So how did they make that leap? I mean, someone had to try it first, right?
Right. There were a few early attempts. Hamburg, Germany, experimented with chlorine in 1893 during a cholera outbreak.
But it wasn't until a few years later that it really took off, right?
Yeah, 1897 in Maidstone, England, is often considered the first time an entire city's water supply was continuously disinfected with chlorine. They basically said, we're going to make this water germ-free.
Germ-free. That's a pretty powerful concept, especially back then.
Totally. It was a revolutionary idea. And they actually succeeded. That really helped solidify the idea that chlorine could be a game changer in water treatment.
And there were other early examples too, right? Like in Belgium.
Yeah, Middelkerk, Belgium, started using chlorine bleach for disinfection around 1902. It was spreading.
Makes sense. Success stories tend to catch on.
Exactly. And then there's a really cool story from Lincoln, England, in 1905. They were hit with a typhoid epidemic, and they decided to try chlorinated lime.
Chlorinated lime. That sounds like old school.
Yeah, it's an early form of calcium hypochlorite, basically. And you know what? It stopped the outbreak, and they continued using it after that.
Wow, that's impressive. So the UK seems to have been pretty forward-thinking when it came to early chlorine disinfection.
Yeah, they were definitely ahead of the curve. The Maidstone success was a big deal. It kind of validated the whole concept. And it's interesting because they were also experimenting with other methods at the same time.
Like what?
Well, in 1906, Nice, France, actually built an ozone disinfection plant. It was one of the first of its kind. So even back then, there was a lot of innovation happening.
So we had the UK with chlorine and France starting to explore ozone. What about London specifically? They were a big city, and they must have had concerns about water quality too.
Oh, yeah. The London Water Board was actively looking for solutions. They relied on long-term water storage for purification, but that wasn't cutting it anymore.
So what did they do?
In 1905, they took the plunge and introduced chlorine disinfection as an alternative to just storing the water. It shows how much things were starting to change.
Makes sense. People were realizing that they needed to be more proactive about protecting their water supplies. So, okay, we've talked a lot about Europe. What about the U.S.? When did chlorine disinfection finally arrive there?
The big year for the U.S. was 1908. That's when they built the first continuous chlorination system at the Boonton Reservoir in New Jersey.
Continuous. What's the big deal about that?
Well, before that, chlorine treatment was more sporadic. It was like a stopgap measure. But this was a prominent system, constantly adding chlorine to the water. It provided ongoing protection, which was a big step forward.
And it was pretty successful, right?
Oh, yeah. And it's thanks to these two guys, Dr. John L. Leal, who came up with the idea, and George W. Fuller, who engineered the whole thing. They used calcium hypochlorite for this system, just like in Lincoln, England.
And then, what, everyone else started copying them?
Pretty much. After that, chlorine disinfection just exploded across the U.S. and around the world. And the results were undeniable.
Like what?
Well, by the 1910s, typhoid, dysentery, and cholera rates were plummeting. In the U.S., typhoid fever cases went from like 100 per 100,000 people in 1900 to almost zero by the 1940s.
That's like a 99% reduction.
Yeah, it's incredible. It's considered one of the biggest public health achievements of the 20th century.
It makes you realize how much something as simple as adding chlorine to water can literally save millions of lives.
Absolutely. It was a game changer.
So we had these large-scale municipal systems starting to use chlorine. But there are also some cool innovations happening for like more specialized uses, right?
Right, like in the military, for example, they needed portable ways to disinfect water in the field.
Yeah, that makes sense.
So in 1903, this army chemist, Carl Darnall, figured out how to compress and liquefy chlorine gas.
Chlorine gas. Isn't that dangerous?
Well, yeah, but it made it way easier to transport and use. And then a few years later, in 1910, William Leicester developed this thing called the Leicester bag.
Leicester bag, what's that?
It's basically a cloth bag that you could fill with water and then add chlorine tablets to. It was a simple but effective way to disinfect and store water for soldiers in the field.
It's pretty amazing how innovative they were back then.
Yeah.
And the technology for delivering chlorine into water systems kept evolving too, right?
Yeah, absolutely. In 1913, they introduced the first continuous chlorine gas dosing device in Philadelphia. It was called the Wallace and Tiernan chlorinator.
So that allowed them to be much more precise with how much chlorine they were adding.
Right. And eventually, by the 1940s, using chlorine gas became way more common than using the older method with powdered lime. It was just more efficient and reliable.
So, as all this is happening, and disinfection is clearly working, I imagine government started to think, okay, we need to set some standards here.
Yeah, that makes sense. It became pretty clear that you couldn't just leave it up to chance. You needed consistent water quality across the board.
So the U.S. was one of the first to jump on that, right?
Yeah. In 1914, the U.S. Public Health Service, or USPHS, published the first ever federal drinking water quality standard. It was a big deal.
And I'm guessing they didn't just stop there.
Oh no, they kept revising and expanding those standards over time. So in 1925, 1946, and 1962, they added more stuff like limits for iron, nitrate, and chloride. By 1962, the standards covered 28 substances.
Wow, that's a lot. They were really getting serious about it.
Yeah, for sure. And then came the really big one, the Safe Drinking Water Act of 1974, or SDWA for short.
I've heard of that. That's kind of a big deal, right?
Huge deal. It basically put the EPA, the Environmental Protection Agency, in charge of drinking water quality. And it also started to address things like disinfection byproducts.
Right. We'll get to those in a bit. But first, this wasn't just a U.S. thing, right? Other countries were setting standards too.
Oh, yeah. This was happening all over the world. The World Health Organization, or WHO, got involved too. They published their first international drinking water standards in 1958.
So they were trying to set minimum standards for everyone.
Right. And then in 1961, the WHO European Office released their own European drinking water standards. They were actually stricter than the global ones.
That's interesting. Why would they be stricter in Europe?
Well, I guess they figured European countries had more resources and infrastructure, so they could aim higher.
Makes sense. So different levels of standards for different parts of the world.
Exactly. And the WHO keeps updating their guidelines. The latest version is called Guidelines for Drinking Water Quality. They're super influential, and a lot of countries base their own regulations on them.
So they're like the gold standard.
Pretty much. And then you have the European Union with their own whole system. Their first drinking water directive came out in 1980.
And what was the point of that?
Basically, to standardize the rules across all the different EU countries. They set limits for all sorts of stuff, from bacteria to chemicals. They've updated it a few times since then, too.
So they're constantly trying to improve and refine the standards.
Exactly. They want to make sure everyone has access to safe, clean drinking water. And they also have specific rules about the disinfectants themselves.
What do you mean?
Well, different countries in Europe have different rules about which disinfectants you can use and how much you can use. Like in Germany, there's a really strict limit on how much free chlorine you can have in the water.
Why is that?
Well, it's kind of a balancing act. You want to kill all the harmful stuff, but you also don't want too much chlorine because it can create byproducts that aren't good for you.
Ah, okay. So it's about finding that sweet spot.
Exactly. Safety first, always.
So let's talk about how we actually treat our water today. What does a modern water treatment plant look like?
All right, so imagine a water treatment plant. Right. It's like a multi-stage process, a bit like an obstacle course for water.
Okay, I'm imagining it. What happens first?
First, you got to remove the big stuff, the solids, the gunk. So they use things like coagulation, sedimentation, and filtration.
So it's like a physical cleaning process.
Exactly. It's like pre-washing your dishes before you actually wash them.
Okay, that makes sense.
And then comes the main event, disinfection. This is where they kill off any remaining harmful microorganisms. It's like the final boss battle for clean water.
And this is where all those different methods we talked about come in, right? Chlorine, ozone, UV, all that stuff.
Yeah, you got it. Chlorine is still the most common method around the world. It's been used for over a century. It's effective against a lot of different bugs, and it's relatively cheap.
And it has that residual effect, right? So it keeps protecting the water even after it leaves the treatment plant.
Yeah, that's a big plus. Chlorine can hang out in the water pipes and keep killing stuff, which is important because you don't want the water getting recontaminated on its way to your tap.
So chlorine is like the reliable old standby. What are some of the downsides? Why even bother with other methods?
Well, chlorine isn't perfect. For one thing, it can react with naturally occurring organic matter in the water and create disinfection byproducts, or DBPs.
And those DBPs can be harmful, right?
Some of them have been linked to health problems, so that's a concern. And chlorine isn't always effective against every single type of microbe. Some parasites, like Cryptosporidium, are pretty resistant to it.
So that's why we need other options.
Exactly. Plus, chlorine gas itself is pretty hazardous to handle, and it can sometimes give the water that, swimming pool smell, which not everyone loves.
Yeah, not the most appealing taste. So where is chlorine still used the most?
It's still super common, especially in larger plants that treat surface water. And a lot of smaller systems that use groundwater rely on chlorine too. In the US, over 60% of water systems use it, and it's also widespread in Europe. It's a workhorse, for sure.
Okay, makes sense. So what about chloramine? How's that different from chlorine?
So chloramine is basically a combo of chlorine and ammonia. They react together to form this compound called monochloramine, which is the one used for disinfection.
And what's the advantage of that?
Well, chloramine is more stable than free chlorine, meaning it sticks around in the water pipes for longer. It's really good at providing that long-lasting residual disinfection, preventing regrowth of anything nasty in the pipes.
It's like a long-range protector.
Yeah, exactly. And it also helps reduce the formation of those pesky DBPs we talked about.
Sounds good. So why not use chloramine all the time?
Well, it's not a superhero. It's actually a weaker disinfectant than free chlorine, so it's not as good at zapping those microbes right away.
So it's more of a slow and steady wins the race kind of thing.
Right. And it's not effective against everything. Cryptosporidium and some viruses can still survive it, so you might need to use other methods like UV or ozone in those cases.
So it's a good backup, but not always the primary solution.
Exactly. And there's another potential issue. Sometimes the ammonia and chloramine can get converted into nitrites and nitrates by bacteria in the pipes.
And are those bad?
Well, they can affect water quality and might be harmful in high concentrations. Plus, chloramine is toxic to fish, so it's a no-go for aquariums. And people on kidney dialysis need to be careful with it too.
So it's got its pros and cons like everything else.
Yeah.
Where is chloramine used most commonly?
It's pretty popular in North America. A lot of big cities in the U.S., like Washington, D.C., San Francisco, and Tampa, use it because it helps them meet those stricter regulations on DBPs. It's used in the U.K. too. And Singapore has this interesting approach where they use ozone or chlorine first, and then they add ammonia to form chloramine in the distribution system.
So they get the best of both worlds.
Yeah, pretty clever. Okay, let's move on to ozone. It's a pretty powerful oxidant, right?
Yeah, I've heard of ozone being used for all sorts of stuff like air purification.
Right. It's super reactive. So for water treatment, they basically create ozone gas by zapping oxygen or air with an electrical discharge.
It's like creating mini lightning bolts.
Exactly. And then they bubble this ozone gas through the water. And because ozone is so reactive, it just tears apart those microbes.
Sounds intense.
It is. Ozone is particularly good at killing those chlorine-resistant critters like Giardia and Cryptosporidium. And it can also break down organic matter in the water, which makes it look and taste better.
So it's a multitasker.
Yeah, it's pretty versatile. And another big plus is that it doesn't leave any nasty chemical residue. The leftover ozone just breaks down into regular oxygen.
That's a good selling point. So what's the catch?
Well, the biggest drawback is that ozone doesn't stick around. It doesn't provide any residual disinfection in the water pipes.
So once the ozone is gone, the water is vulnerable again.
Exactly. So usually they have to add a little bit of chlorine or chloramine after the ozone treatment to keep the water protected as it travels through the pipes.
Makes sense. It's like a 1-2 punch.
Right. And there's another potential problem. If the source water has bromide in it, ozone can create this byproduct called bromate.
And bromate is bad.
Yeah, it can be. It's been linked to some health issues, so if you're using ozone, you have to be careful about that. And ozone systems are generally more expensive to install and operate than chlorine systems.
I can see how that would be a limiting factor.
Yeah, it's not the most practical option for every water system. It's more common in larger, well-funded systems.
So where do we typically see ozone being used?
It's super popular in Europe, especially in France, Germany, and Italy. They often use it as the primary disinfectant, followed by a small dose of chlorine for that residual protection. In the U.S., it's becoming more common in big cities like Los Angeles, Dallas, and Milwaukee, and they've used it to combat Cryptosporidium outbreaks.
Interesting. So ozone seems like a good option for those larger, more advanced systems.
Yeah, definitely. It's a powerful tool in the fight for clean water.
Okay, last but not least, let's talk about UV disinfection. This one's a bit different because it doesn't involve any chemicals, right?
Right. It's all about using UV light, specifically UVC light. It's that high-energy stuff that can damage DNA.
So it basically fries those microbes from the inside out.
Pretty much. It scrambles their genetic material so they can't replicate and make you sick. And UV is really good at killing those tough cysts like Cryptosporidium and Giardia, which chlorine and chloramine sometimes struggle with.
So it's like the heavy hitter.
Yeah. And because it doesn't use chemicals, it doesn't create those DBPs. Plus, it doesn't change the taste or smell of the water.
That's a bonus. So it sounds like a win-win. What are the downsides?
Well, just like with ozone, UV doesn't provide any residual disinfection, so you still might need to add a little chlorine or chloramine after the UV treatment.
Ah, so that's a recurring theme.
Yeah, it's a challenge.
Hmm.
And UV light can only do its job if the water is clear. If it's cloudy or has a lot of color, the light can't penetrate effectively.
So you need good filtration before the UV treatment.
Exactly. And some viruses and bacteria can be pretty resistant to UV, so you might need higher doses, which can be energy intensive. And of course, it all relies on having a reliable power supply.
So it's not without its limitations. Where is UV disinfection used most?
It's gaining popularity all over. Big cities like New York City and Paris use it, and in some European countries, like the UK, Netherlands, and Denmark, they're so good at UV disinfection that they can often skip the chlorine altogether, even in the distribution system.
Wow, that's impressive.
Yeah, they have really clean and well-maintained pipes, so they can rely on UV alone. And in Turkey, they're starting to use UV more in smaller communities, especially for groundwater sources.
So it's a versatile method.
Yeah, definitely.
Looking back at all these different methods, it's amazing how far we've come. It really shows how much we've learned about protecting our drinking water.
Yeah, it's a testament to human ingenuity and our understanding of science. It's also a reminder that there's no one-size-fits-all solution. The best method depends on the specific situation.
Right, it's all about adapting to the challenges. So, stepping back for a moment, it's clear that water disinfection is like one of the most important things we do for public health.
No doubt about it. It's probably saved more lives than almost any other public health intervention. I mean, think about all those horrible epidemics of cholera and typhoid that used to ravage cities.
Yeah, it's hard to imagine what life was like back then.
It was brutal. But chlorination, along with filtration, basically wiped those diseases off the map in developed countries. The CDC even says that clean water and disinfection were major factors in increasing life expectancy in the 20th century.
Wow, that's a pretty big claim.
It's true, and Life magazine even called disinfected drinking water the most important public health development of the millennium.
That's a pretty bold statement.
It is, but it's hard to argue with the impact. And it's not just about preventing those big outbreaks. Disinfection also keeps our water safe every single day.
Right, because even a small amount of contamination can cause problems.
Exactly. That's why those residual disinfectants like chlorine and chloramine are so important. They keep the water safe as it travels through the pipes, preventing recontamination.
So it's like a constant safeguard.
Right. And water treatment plants constantly monitor the levels of disinfectants in the water, and they test for bacteria to make sure everything is working properly. It's a really rigorous process.
It's good to know someone's looking out for us.
Yeah, for sure. And it's easy to take safe water for granted, but the reality is that billions of people around the world still don't have access to it.
Yeah, it's a global issue.
The WHO estimates that billions of people are drinking water that's contaminated with fecal matter.
That's awful.
It is, and it leads to all sorts of diseases like cholera, diarrhea, and typhoid. It kills hundreds of thousands of people every year, mostly children.
So water disinfection is literally a matter of life and death for many people.
Absolutely. That's why the UN has this goal of providing safe and affordable drinking water for everyone by 2030. And scaling up disinfection is a huge part of that.
It's a massive challenge, but hopefully we can make it happen.
I hope so. It's a basic human right.
Okay, so we've covered a lot of ground here. We've gone from ancient methods to modern technology. It's been a fascinating journey.
Yeah, it really shows how much we've learned and how far we've come. From simple things like boiling water to the sophisticated ozone and UV systems.
And even though we have all these new technologies, chlorine is still a key player.
Yeah, it's still a workhorse, especially in those larger systems. But ozone and UV are becoming increasingly important. They're like the specialists that come in and deal with specific problems.
And it seems like the best approach is often to combine different methods.
Absolutely. It's all about tailoring the approach to the specific situation. But no matter what, disinfection is non-negotiable. It's the foundation of safe drinking water.
And it will continue to be crucial as we face new challenges in the future.
For sure.
So there you have it, folks. A deep dive into the world of drinking water disinfection. It's been a long one, but hopefully you've learned something new.
And hopefully you'll never take a glass of clean water for granted again.
Exactly. It's something to be grateful for. So, as always, don't forget to subscribe to the Environmental Science and Engineering podcast channel for more deep dives on all sorts of fascinating topics. And feel free to leave a comment below with your thoughts or any questions you might have. We love hearing from you.
Absolutely. We appreciate your support.
And until next time, stay curious, stay informed, and stay hydrated with some safe delicious drinking water.
Bye for now. See ya.